you can go for the video lecture, or you can take the help of some books also. So this is the last chapter, and it will take 2 lectures to finish this chapter or this unit, you can say. Okay. So semiconductors. Hmm? Semiconductors. There are, we know there are conductors, there are insulators, and semiconductors are also there. So what are the conductors? So conductors have high conductivity. Hmm? Insulators have very low conductivity. Semiconductors have the conductivity in between conductors and insulators. So semiconductors are those materials which have conductivity between conductors. Conductors, we know silver is a good conductor of electricity, copper is the best conductor of electricity, and insulators, insulator means glass is an insulator, diamond is also an insulator, wood is also an insulator. So basically we can say semiconductors are those materials which have conductivity between conductors and insulators. Now the question is why semiconductors are important. Why semiconductors are important? So two reasons given here. Uh, Semiconductors have two important properties. Semiconductors have two important properties. Number one, with the help of semiconductor, we can control the number of charge carriers. Number of charge carriers. What is the meaning of number of charge carrier? Which constitutes the electric current in the material. So uh, can control the number of charge carriers, or we can control the conductivity of the material. Okay. This we cannot do in case of the uh, conductors. Conductor have the fixed conductivity. We cannot change the conductivity of the conductor. Change means if we will change, we have to either increase the temperature or decrease the temperature. That is another thing. But here we can control the charge carrier basically. We can control the charge carrier, and we will see this also. Second point, with the help of the semiconductor, we can get the unidirectional current. We can get the unidirectional current in one direction. So what is the meaning of unidirectional current? So in case of conductors, case of conductors, suppose we have this conductor. This is a conductor. You can say this is a copper conductor. So in this copper conductor, the current will flow like this, in this direction and in this direction. And also the current will flow in this direction. So in conductors, in both the direction, the current will flow. Current will flow in both the direction. But we can control one direction current. We can control one direction current in case of the semiconductor. Okay, we can control the current in one direction. Now, examples of semiconductor, elemental form. In elemental form, we have silicon and germanium. We have silicon and germanium. Silicon and germanium. These are the semiconductors in elemental form. In compound form, we have gallium arsenide, GaAs, indium phosphide. So these are inorganic. We have anthracene, polyaniline, etc. These are organic. These are the organic. So what is here? Here is, you can see, semiconductors are those material which have the conductivity between conductors and insulators. And why the semiconductors are important? Number one, with the help of semiconductor, we can control the number of charge carriers. Or charge carrier constitutes the conductivity. So we can say conductivity can be controlled, and it can give a unidirectional current. Examples of semiconductor: silicon, germanium, elemental semiconductor; compound semiconductor, gallium arsenide, indium phosphate. These are inorganic. And in organic, we have anthracene and polyaniline. Anthracene and polyaniline. Now the most important part is the energy band in crystals. Energy band. Energy band in crystals. So we know that in an isolated atom, uh, the energy of an electron is fixed. Because according to the Bohr's model, the energy of an electron revolving in a particular energy level is fixed, according to the Bohr's theory. According to Bohr's theory, in an isolated atom, the energy of the electron depends on the orbit in which the electron is revolving. So this is the way to represent the energy levels of electron revolving in different energy levels. So for n is equal to 1, mean for the first orbit. In first orbit, the energy of the electron will be minus 13.67, 13.6 electron volt. I told these things in the last classes, in the chapter atom, when we were discussing the force model of atom. I don't know whether you were present in the class or not, but I told. For n is equal to 2, means first excited state, the energy will be this. N is equal to 3, the energy will be this. N is equal to 4, the energy will be this. So we can say, in an isolated atom, the energy of the electron revolving in different energy level will be a fixed value. So in an isolated atom, discrete energy levels are present like straight line. So we will represent the energy with the help of this straight line. This straight line means only one energy level is there. After that, when the crystal means crystal is made up of atom. So we can say that when atom come closer, then there is a formation of the crystal when atom come closer. And when atom come closer, so electrons of one atom and electrons of another atom will interact. And if this will happen, then energy of the different electrons of different atoms will be affected. Okay. So atoms come close in a crystal. Atom come close approximately 2 to 3 angstrom. 2 to 3 angstrom. 1 angstrom is 10 to the power minus 10 meter. So they are very close to each other. Talking about the two atoms. So atoms come close 2 to 3 angstrom and electrons have some new interaction. So when the atom will come close, electrons will have new interaction with electrons of the neighboring atom, with nucleus of the neighboring atom. You can see these two, this is atom 1, this is atom 2. Okay. For the formation of the crystal, atoms are coming closer, approximately to a distance of 2 to 3 angstrom. So this is one atom, this is another atom, this is the electron, this is the electron of this atom, this is the electron of this atom. So both these electron, there will be an interaction between this electron and this electron. There will be an interaction between this electron and this nucleus. There will be an interaction between this electron and this nucleus. Means there will be some foreign interactions. Okay. Now the energy of the electron in a particular orbit will not be fixed. Okay. In a crystal, each electron has a unique position. Hence, each electron has in a crystal, each electron has a unique position. Hence, each electron has a unique interaction. So imagine the crystal, and inside the crystal there are atoms. So you can imagine that each and every atom have different position. Means each and every atom will be surrounded by different number of atoms. So you can say each electron in that atom will have different position with respect to the crystal or with respect to the atom. If different electrons are surrounded by different number of atoms, so the energy level of the electron will be different. So you can see here in a crystal, each atom has unique position. Each atom has a unique position. Hence, each electron has unique position because each atom will be surrounded by different number of atoms. So each has unique energy interaction. Now this is very easy. So each electron has unique energy interaction. Hello, Nafisa. Now it's fine.
Yes, sir, it's fine.
Okay. So you have to remember this line. Electron has unique energy interaction. So what we are doing means what we are studying. We are studying how the energy band will form. How the energy band will form. And what is the meaning of the energy band? Their energy band means the continuous energy levels. The continuous energy level we will get. And the reason I am telling why we will get the continuous energy level, because each electron in a atom Or in a crystal, there are many atoms, and each atom have different positions, so each electron will have different positions, so each electron will have different energy interaction, so each electron will have different energy level. So now energy of the electron will not remain fixed. For n is equal to 1, the energy of the electrons which are in n equal to 1, they do not have the same energy now. Okay. They have different energies. They have different energy levels. Okay. So each electron have different energy level when they belong to same subshell of the isolated atom. Okay. Now see this. This is 1s, 2s, 2p, 3s, 3p. Basically, this is the energy showing. This is the energy level for the isolated atom. This is for isolated atom. When with the help of the isolated atom, the crystal will form. The crystal will form. So these energy band will form. When there is the crystal will form, because in the crystal there are many atoms, and there, so in those atoms there will be the electrons. Okay, there will be electrons, and each electron will have different energy. So basically, due to that, these energy bands will form. Basically, here will be one energy level, here will be one energy level. So they are continuous energy level. In the subshell, there are electrons. In subshell, there are electrons, and each electrons have unique energy interaction. So suppose the electrons of 2p subshell, each electron of 2p subshell will have different energy level, and these continuous energy level is basically the energy band. You can see this diagram. Here is this the individual atom. Okay. So if the atom is the individual, then this is the fixed energy. Okay, this is the fixed energy, discrete energy level or stage. When the crystal will form, atom will combine. So there will be number of electrons in a subshell. Okay, there will be number of electron in a subshell. Suppose in 2s subshell, the electrons will be there. Okay, the electrons will be there, and for those electrons, the energy interaction will be different. So basically, the energy interaction will be different. So you can say energy level will be different, and those energy level will be continuous. And this is the formation of band, or you can say energy band. Now, suppose this is 3s. This 3 in 3s. Suppose this is 3. This 3s is half filled with electron, and half is empty. Half filled with electron, half filled with half is empty. So this is known as the conduction band. This is known as the conduction band. We will discuss the conduction band and the valence band once again. Conduction band. And this is the valence band. Now, for each electron of isolated atom, single atom, in 1s, 2s, 2p, 3s have fixed energy. Okay, in case of the isolated atom, in 1s there will be electrons, in 2s, 1s2, 2s2, 3p6. You know the electronic configuration. Suppose sodium is given Na. What is the atomic number of sodium? 11. So the electronic configuration, how you will write? 1s2, 2s2, 2p6, okay, 3s1. So there are electrons in S, 4 electrons in S, 6 electron in P. Means 2 electron in 1s, 2 electron in 2s, 6 electron in 2p, 1 electron in 3s. Okay. If this is an isolated atom, so the electrons that are present in 2s, 2p, 1s, 3s, 3p have the same energy. But when the crystal will form, so the number of electron which is present in 2s, 2p, 3s have different energies, and those energies in continuation will form a band. So for each electron of isolated atom in 1s, 2s, 2p, 3s have fixed energy. And one more thing, the inner electron nearly remain unaffected by the neighboring atom. The inner electron nearly remain unaffected by the neighboring atom. So you can see here, these are the shells. Suppose here is this inner electron. So now this electron is inner electron. So on this electron, there will not be much effect by the electrons here or by the nucleus of the other atom, because this is the inner electron. So it is found that on the inner electron, the interaction is negligible. Okay, the inner electron in terms of the energy is not much deviated. Why the energy? Why there is a form? Why there is a formation of energy band? Because in an atom, we know, uh, in an atom, in a crystal, there are large number of atoms, and in those atoms there are electrons. And I told you, for each atom in a crystal have different unique energy interaction. So you can say the electron will have the unique energy interaction. Now electrons are found in these subshells 1s, 2s, 2p, 3s. So in these, all the electrons have different energy interaction. So they will have different energy level, and when those energy level, you can say the energy levels in continuation is a band basically. So you can say energy lines basically these here you will have energy lines like this: one energy line, 2, 3, 4, 5, 6, 7, 8, like this. Millions of energy lines you will have, and these lines will be very close, so it is becoming a band. So energy lines, and these energy lines will be of electrons present in 3s. So energy line placed very close, to each other, which appears a band. This chapter is a little bit conceptual, which appears. Prior knowledge is also required in this chapter, which appears a band, a energy band. See, this is one energy line, another energy line, another. So when these lines will be very close, so what it will become? It will become a band, no? It will become a band, and each energy line will representing the energy of electron. And I told you energy of each electron will be different. in a particular subshell? So this is for the hydrogen. Sorry, sodium. But in 1s, there are 2 electrons in 2s. This is fully filled. This is also fully filled. You can say 2s2. This 2p6 is also fully filled. This 3s is half filled. Hmm? Because there can be 2 electrons, but here is only 1 electron. So I have shown this is as half filled. So I think there is no requirement of this. Now valence, what is valence band? What is for conduction band? And what is forbidden energy gap? So basically, this is the energy. This line is showing the energy. Okay, this line is showing the energy. And this is the conduction band. I told you the concept of band. This is conduction band. This is valence band. Conduction band, valence band. So in valence band, there will be electrons. Valence band we have seen for take the case of sodium. We have seen this valence band is completely filled with electrons. So electrons are there, completely filled, and this conduction band can be completely filled or can be partially filled. And this energy gap between two bands is known as the forbidden energy gap. Forbidden energy gap. So this is very important. You have to remember. I have also written the definitions. So before that, you should know this. This is the minimum energy of the conduction band, and this is the maximum energy of the valence band. This line is representing the maximum energy of valence band. This line is representing the maximum energy of minimum energy of the conduction band. And difference of these will be the forbidden energy gap. Now we will see the definition of valence band first, then conduction band. Now valence band. Range of energies possessed by valence electron in a crystal. Okay, range of energies possessed by valence electron in a crystal. It contains valence electron. The valence band electrons do not participate in electrical conductivity. So remember, basically, what is a band? Band is a range of energies. Okay, range of energies. Okay, in continuation, range of energies in continuation, and with the help of that, you will get a band. Basically, this band is containing energies, energy levels. So range of energies possessed by valence electron in a crystal. So basically this band is formed due to the electrons in the valence band. So you have to remember what is the valence band? Range of energies possessed by valence electron in a crystal, and in valence band there will be valence electron. So it contains valence electron. And one more thing, these valence electrons are not free electrons. These valence electrons are not free electrons. These are involved either in the bond formation. Okay, these are involved in the bond formation. So if these are involved, the electrons of the valence band are involved in the uh, bond formation. So these electrons are not free electrons. So these will not participate for the conductivity, for the electrical conductivity. The electrons in the conduction band are the free electrons. So now what is conduction band? The band above the valence band, the band above the valence band. Range of energies possessed by the electron in a uh, range of energies possessed by free electron in in a crystal. Electrons may or may not exist here. So I told you that may the electron will be here or it cannot be here. Okay. Conduction band electrons are responsible for electrical conductivity. So the electrons which are present in the conduction band are the free electron, and due to the free electrons there is a electrical conductivity. Now forbidden energy gap. Forbidden energy gap is basically the difference between EC and EV. So forbidden energy gap, some energy levels in between valence band and conduction band are forbidden for electron. These energy level together known as forbidden energy gap. So in between the conduction band and the valence band, here also there are some energy level, but in these energy levels the electron cannot be found. Okay, and these energy band are forbidden or restricted for the electrons. That is why these are known as the forbidden energy gap. And what is the value of the forbidden energy gap? It will be it will be Eg. Eg means the forbidden energy gap, that is equal to EC minus EB. You can say it is the minimum energy of conduction band minus maximum energy of the valence band. So from here, the electron, we can give the energy to the electron, and electron can jump from valence band to the conduction band and participate in the electrical conductivity. Now we will see the difference between the conductor, semiconductor and insulator on the basis of the conduction band and the valence band. So for the conductors, the conduction band and the valence band overlaps. The conduction band and the valence band overlaps. So you can see here valence band and conduction band overlaps, and this energy gap, there will be no energy gap. There will be no energy gap when they will overlap. Means the electron of the valence band will be present in the conduction band, or the electron from the valence band easily move to the conduction band even at the room temperature also. So electron readily move to readily move to conduction band from valence band and conducts electricity. In case of the semiconductor, this is the conduction band, this is the valence band. This is the conduction band, this is the valence band. So there is a difference between the conduction energy of the conduction band and valence band. Means there is a forbidden energy gap between the valence band and the conduction band, and that forbidden energy gap for the semiconductor is less than 3 electron volt. Taking example, for silicon semiconductor, this energy gap is approximately 1.1 electron volt. For germanium, this EG is 0.74 electron volt. So to move the electron from valence band to the conductor to the conduction band, there is a requirement of energy. Okay. So electron on absorbing heat from the surrounding jumps from valence band to the conduction band. So at room temperature or from the surrounding, the electron present in the valence band will get the energy and will jump from valence band to the conduction band. And when the electron will be in conduction band, it will be free, means responsible for the electrical conductivity. Now come to the insulator. In case of the insulator, this Eg is greater than 3 electron volt. For example, for diamond, the forbidden energy gap is 6 electron volt. This energy gap or forbidden energy gap is increasing. So it has to heat at high temperature to excite the valence bond electron to conduction band. Means more amount of heat you have to give to the valence band electron so that it has to move to conduction band. For moving one electron from valence band to the conduction band, more amount of heat energy or energy is required because this energy gap is large as compared to the semiconductor. Okay, but in case of the conductor, it is zero. Okay, so please take the screenshot, Nafisa and Nabal.
Yes,
So
sir.
this is the basic introduction of the semiconductors and the energy band. Okay. Okay, take the screenshot.
Yes, sir.
Okay. Okay. Take this screenshot. Done?
Yes, sir.
Okay.
Yes, sir. Done. Yes, sir. Done. Done, sir. Done, sir.
Okay.
Yes, sir. Done.
Okay.
Yes, sir. Done. Done, sir.
Okay.
Done, sir.
Okay.
Done, sir.
Okay. Now difference. This can come in your exam. This is very important for exam point of view. Difference between the conductor, semiconductor, and insulator, and they can ask you explain with the help of the energy band. So for the conductor, the conduction band and the valence band overlaps, so energy gap is zero. For the semiconductor, this gap is moderate, means the energy gap is basically you can say less than 3 electron volt. For the insulator, this energy gap is large, that is greater than you will get 3 electron volt. Okay. So now from here to now, both the conduction band and valence band are overlapping. Overlapping means the electron is present in conduction band at the same time and it is presenting in the valence band at the same time. So you can say that electron can easily move from valence band to conduction band. If electron and when the electron is in the conduction band, okay, what who is responsible for the conductivity? Electrons in the conduction band. Okay, so when the electron from the valence band to the conduction band, when the electron from the valence band will move to the conduction band, so there will be the more electrical conductivity. That is why the conductors have the maximum electrical conductivity, because the conduction band and valence band overlap and the electrons from the valence band can easily move to the conduction band. But in case of semiconductor, this gap is moderate. So we have to give some energy so that the electron should move from valence band to the conduction band. Okay, so that is why the conductivity of semiconductor is less than that of conductors. Okay, but in case of insulator, this energy gap is even more than the semiconductor. So that is why the conductivity of insulator is least as compared to the semiconductor and conductor. So now you can take the screenshot of this. And I have given the reason also why these bands are forming. Because electrons in a crystal, each electron in a crystal have different energy interaction. So they have different energy level. And when you will combine those energy level, you will get a band of energy. Basically, this is a band of energy. Okay, take the screenshot.
Yes, sir. Done.
Okay,
Yes, sir. Done.
okay.
Yes, sir. Done.
Now here you have to focus. Both of you, you have to focus here. This is a little bit conceptual topic. Hmm. To understand the mechanism of the intrinsic semiconductor, Okay. Okay. So just a minute. Okay. So in case of the intrinsic semiconductor, first of all, what is intrinsic semiconductor? Intrinsic semiconductor means the pure semiconductors, like pure silicon, pure germanium, without any impurity. Okay. Pure silicon, pure germanium. Silicon is having an atomic number of 14, and when you will do the electronic configuration, it is 1s2 2s2 2p6 3s2 3p2. So this shell, third shell, will be the valence shell, and this 3s and 3p is a subshell. 3 is a shell. So this is a valence shell, and how many electrons are there? These numbers are representing the electrons. How many electrons are there in a valence shell? 4 electrons. In case of the silicon semiconductor, pure silicon. In case of a pure germanium, this is atomic number 32. So the electronic configuration will be 1s2 2s2 2p6 3s2 3p6 3d10 4s2 and 4p6. And 4 is the valence shell. How many electrons are there in a valence shell? 2 plus 2, 4 electrons. So basically, silicon and germanium are from the carbon family. CSI, okay, like this, na? Carbon, after that silicon, germanium, tin, lead. Okay. So now you can see in case of the pure silicon and pure germanium, what are they? They are intrinsic semiconductor. So you can see in the silicon and the germanium, both have 4 valence electron. So both have the 4 valence electron, and and all these electrons are involved in covalent bond formation in silicon and germanium crystal. We know that carbon forms the covalent bond. Covalent bond means the bond formation due to the sharing of electron. Hmm? So carbon have the tendency, and these silicon and germanium are from the carbon family, so they can also form the covalent bond. So these 4 electrons na, of valence shell are involved in the covalent bond formation. Covalent bond formation. You can see here. This is a silicon crystal. Silicon crystal. Okay, so in silicon crystals, there will be silicon atoms bounded by the bond. Okay, okay. So how silicon is forming the bond? You can see here. This is silicon atom, silicon, 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 silicon atom. In the valence shell, how many electrons are there? 4 electrons. So 1 electron, 2 electron, 3 electron, 4 electron. This negative is representing the electron. 1 electron, 2 electron, 3 electron, 4 electron. 1, 2, 3, 4. 1, 2, 3, 4. Here also 1, 2, 3, 4. Here also. And these 4 electrons are from the valence shell. So these electrons are known as the valence electron. These electrons are known as the valence electron, because these electrons are in valence shell. So these are known as the valence electrons. Okay. Now this is the covalent bond. This silicon and this silicon is forming a covalent bond, and covalent bond is formed by sharing of electron. So one electron of this silicon, one electron of this silicon. So by sharing, there is a formation of covalent bond between this silicon and this silicon. Similarly, between this silicon and this silicon, there is a covalent bond. So basically, this is representing a covalent bond. Okay, this is a covalent bond. And covalent bond is formed by the sharing of the valence shell electron. And these are the valence electrons. So this is the silicon crystal structure and how there is a bonding in that. Now we will try to explain this, the structure of this with the help of the energy band. Hmm? For the semiconductor, this is a semiconductor. This will be the valence band, and this will be the conduction band. And there will be the forbidden energy gap. Okay, there will be the forbidden energy gap. Earlier we discussed how uh, valence band and conduction band are there for the semiconductor. So in the valence band, okay, in valence band, there will be the electrons. Hmm? There will be now I am talking about crystal, not a single atom. So in valence band, there are large number of electrons. There are large number of electrons in a valence band. So in a valence band, there will be electrons, but in conduction band, there will be no electron. At, if I am talking about at 0 Kelvin, why there is no electron at 0 Kelvin in conduction bond? Because all the valence shell electrons are involved in the covalent bond formation. So no electron is free here, and in covalent bond there are free electrons. So that is why at 0 Kelvin there is no electron or no free electron in covalent bond. This is written the this gap for silicon. This is this for germanium. This is this. So if you will give this much of energy for this to this electron, then the electron will move from the valence band to the conduction band and will contribute to the electrical conductivity. But at 0 Kelvin, there is no electron in conduction band because all the valence shell electrons are involved in the covalent bond formation. So at 0 Kelvin, the silicon is insulator. Silicon will not conduct electricity at 0 Kelvin. Now you know the reason. Why? Because in at 0 Kelvin, there is no free electron in conduction band, or there is no free electron. So at absolute zero temperature means 0 Kelvin, there are no free electrons in the conduction band, as all the valence electrons are involved in covalent bond formation. A semiconductor behaves as insulator at 0 Kelvin. Okay. On increasing the temperature, more and more thermal energy is available. Some covalent bonds may break and some free electrons are generated. Now, when you will give energy to this silicon crystal, so there may be some formation of bond. There will be some breaking of bond. So when this bond will break, the electron will become free. So there may be some free electrons due to the breaking of bond. When you will supply the energy, the bond will break and electron will become free. And when the electron will become free, it can move to the conduction band. And when it will move to the conduction band, it will become free. And due to the free electron, there will be the electrical conductivity. So on increasing the temperature, more and more thermal energy is available. Some covalent bonds may break and some free electrons are generated. Now, this is the condition of the silicon crystal or for the semiconductor at 0 Kelvin. Now we will talk what will happen at the room temperature. So at the room temperature, at means 27 degrees centigrade is the average room temperature we take. So one covalent bond breaks in 10 to the power 9 atom. Means at a room temperature there will be some heat energy. Due to the room temperature there will be some energy. So due to that energy only one covalent bond will break out of 29 atoms. Suppose here there are 10 to the power 29 atoms are there, and they all are involved in the bond formation. Okay, suddenly you have taken this to the room temperature, only one covalent bond will break. Only one covalent bond will break at room temperature out of 10 to the power 29 atoms. So when the covalent bond will break, this will be the condition then. Suppose here this covalent bond break due to the room temperature. So this covalent bond will break, and this electron, this is the free electron now. Now there is no more sharing of electron. Now this electron is not involving in the bond formation. This electron is now not involving in the bond formation. So due to the thermal energy of the room temperature, this electron becomes free. So that is why this electron is known as thermally generated free electron. And earlier this electron was here. Okay, earlier this electron was here. Now when the electron will be removed from here, there will be a vacancy. There will be a vacancy, and this vacancy is known as hole. This is known as the hole. So basically what will happen? At room temperature, some covalent bonds will break, electrons will become free, and due to the electrons will become free, there will be some vacancies created, and those vacancies are known as holes. So this is a new concept in the semiconductor. With the help of the energy band, you can understand this. This is a valence band, this is a conduction band for the semiconductor. And this is the energy band gap, forbidden energy band gap. At room temperature, so this is the band diagram at room temperature. At room temperature. At room temperature means 227 degrees centigrade. So at 27 degrees centigrade, at 27 degrees centigrade, what will happen? Some bonds will break, an electron will become free, and these bonds are breaking. These are the these electrons are the valence band valence shell electron. Okay, so these electrons are the valence shell electron, and when due to the energy this bond will break, this electron will become free, and this electron when become free will move to the conduction band. Now here will be a hole. Okay, so suppose this electron become free, so at this position there will be a hole. From here one electron become free, here a hole will generated. So here also you can see, due to the room temperature, some electrons will become free. Those electrons will move to the conduction band, and the remaining vacancy will be hole. So what is hole? Hole is a vacancy due to thermally generated free electron, and holes are positively charged. Basically, hole is nothing, just a vacancy created by the electron. Electron is a negatively charged. Electron is a negatively charged. When the electron will remove, an equal amount of positively charged will be there on the vacancy. Okay, so you can understand this like this. So electron, when you have given the temperature to the electron, the covalent bond will break and electron will become free, and a hole will be created, and both have the equal charge. Electron will have a negative charge and hole will have a positive charge, but charge of both, magnitude of the charge will be equal for hole and for electron. Now we have two things. One is hole, one is electron. Now in case of the semiconductor at room temperature, what will happen? Some covalent bond will break, free electrons will be generated and hole will be generated. Okay. And electron is negatively charged, holes are positively charged. So number of thermally generated free electron means the electrons that are generated at the room temperature. So number of thermally generated free electrons is equal to the number of holes. Obviously, the this the number of electrons will be equal to the number of holes now. So if the one electron is become free from here, so here one hole will generated. If four electron from this structure are becoming free, so there will be four holes, there will be four vacancies. So number of holes and the number of free electron generated will be same. So number of electron per unit volume, number of holes per unit volume, basically both will be equal. So we can say this equal to this and this is equal to n suffix I. N suffix I, number of intrinsic charge carrier. Basically holes and electrons are the charge carriers. Holes and electrons are the charge carrier in a semiconductor, in a pure semiconductor or intrinsic semiconductor. So this is true for the intrinsic semiconductor. And what is n? Number per unit volume. So Ni is representing the intrinsic charge carrier density, or this is also known as charge carrier per unit volume. So in unit volume, how many charge carriers are there? That is equal to Ni. Now at room temperature, it is found that uh, in, intrinsic charge carriers or charge carrier in a pure semiconductor is 2.4 into 10 to the power 19 per meter cube. In 1 meter cube, there are 2.4 into 10 to the power 19 charge carriers for germanium. For silicon, the number is 1.5 into 10 to the power 16 per meter cube. So basically, these charge carriers will depend upon the temperature. When you will increase the temperature, more bond will break, more number of thermally generated free electron will be there, more number of hole will be there. On increasing the temperature, the charge carrier in a pure semiconductor will increase. So this is depending upon this expression. So basically, number of intrinsic charge carrier is directly proportional to E to the power minus Eg. Eg is forbidden energy gap. K is the Boltzmann constant. T is the absolute temperature. And this type of graph you will get. On increasing the temperature, intrinsic charge carriers are increasing. Now we have holes and we have electron. Now in the semiconductor, in case of the pure semiconductor, there are thermally generated free electrons and there are holes. So the current in the semiconductor will be due to the electron motion and due to the hole motion. And we will see how there will be the electron motion and there will be the hole motion in case of the semiconductor. So first is the current due to electrons. Current due to electrons. So suppose the electric field you have applied in the semiconductor, you will apply the electric field. Like in case of the wire, you apply the electric field, then only there will be the current flowing in the wire. In the same way, when you will apply the electric field to the semiconductor, okay. So due to this electric field, this electron is negatively charged. The electric field is in this direction, so electron will move in the opposite direction, and the current due to electron will be in this direction, because current is always in the opposite direction of the motion of electron. So current due to electron will be in this direction, in upward direction you can take. Now we will see the current due to hole. So now see the mechanism of how the holes move. Basically, in actual, holes does not move. Holes do not move in actual. So holes apparently move in the direction of the applied electric field. How? So these are the two diagrams. Suppose you have applied the electric field in this direction. You have applied the electric field in this direction. So due to this electric field, what will happen? The electron from anywhere. Suppose take this electron. This is the electron, and you have applied the electric field. So due to this electric field, due to this electric field, this electron, okay. Earlier here is one hole. Here is one hole due to the room temperature. We know at room temperature there are holes and thermally generated electrons. So initially this is the condition. Here is one hole. Here is one hole. And why this hole is there? Because of the room temperature. So there is one hole, and this is the electron here. Here is also electron. Here is also, there are so many electrons, but we are focusing on this electron and this hole. So due to this, when you will apply the electric field, so due to this electric field, this electron will move from here to here. This electron, this valence electron will move from here to this hole, okay. And when the electron and hole combine, okay, here the electron and hole will combine. So this is the vacancy, basically hole is a vacancy. So this electron will take this vacancy, okay, and form the covalent bond with this silicon, okay. But here a new vacancy is created, you can see here. So that is why holes are moving. That is why you can, it is appearing that the hole are moving in the upward direction, but in actual the valence shell electrons are moving. So due to the electric field, this valence shell electron is moving, okay, and it is appearing that the hole is moving. Why? Because when the valence shell electron will move, the vacancy will be created. So we can say holes are apparently moving. Understanding?
Yes, sir.
Hmm. So due to this electric field, there will be some electric force on this electron, and this electron will move from here to here. And this hole is already generated due to the room temperature. And what is this hole? Hole is the type of the vacancy created by the thermally generated electron. So means earlier what will happen here? What happened here? Earlier, earlier due to the room temperature, one electron is removed from here. So that is why this hole is formed. Now what is happening? You have applied the electric field. The nearby electron will move from here to here. Why this electron is moving? Because on this electron there is an electrostatic force. Now this electron will come here. Now this become like this. So here this silicon atom, okay, this electron will come here. Both these electrons will form the covalent bond. And now here, because this electron is moved here, here will be a hole or a vacancy. So you can see here the hole is moving in the hole is appearing to moving in the upward direction, but in actual the valence shell electrons are moving. So electric field you have applied in this direction, holes are also moving in this direction, from here to here. Holes are also moving in the direction of the electric field. So holes are positively charged. So direction of the positive charge motion is the direction of the current. So current due to hole will be in this direction. So now you can see here the current, direction of the current due to hole and direction of the current due to electron is same. Now with in terms of the energy band, you can also understand in terms of the energy band. Okay. So basically this is the conduction valence band. and this is the conduction band at room temperature. I told you that at room temperature in the conduction band there will be some thermally there will be some thermal electron, you can say thermally generated electron at room temperature, and here will be in the valence bond, in the valence band there will be holes. I told you where. Here I told you na, at room temperature some electron will move from here to here, so here there will be vacancy created, that is hole. So this is the condition of the room temperature, and these are the thermal electrons. Suppose you have applied the electric field in this direction. So due to these thermal electrons are moving in this direction. These thermal electrons are moving in this direction. Thermal electrons are moving in this direction. Okay, moving from valence band to the conduction band. So due to the thermal electron, the direction of the current will be this. Due to the electron, direction of the current will be this. Now in valence band, what will happen? You have applied the electric field, and due to that electric field, earlier I told you what will happen. Due to the applied electric field, the electron will occupy hole. The electron will occupy hole, and new vacancy will be created. Same is the case here. This electron, due to the electric field, will occupy hole, and here a new vacancy is created. So these electrons will occupy the hole due to the electric field. Why? Because on electron there is a electric force. So due to that, this electron will move to hole, and here new vacancy is created. Here. Means now hole is generated here. Again, what will happen? Due to the electric field, these electrons will occupy these vacancies, and here holes will generate it. So holes are moving. Holes are moving. Holes are appearing to moving in this direction. So holes are appearing to moving in this direction. So current due to hole will be also in this direction. So net current will be due to the electron and hole. So IE is what? Due to current due to thermally generated free electrons. And IH is what? Due to apparent motion of holes or actual motion of valence bond electron. In actual, what is happening? These electrons are moving, na? These valence band electrons are moving. Holes are not moving. Holes are appearing to move. Because of the electric field, these valence band electrons are moving and vacancy is creating. So due to apparent motion of holes or actual motion of valence bond band. Okay, and one more thing, the current due to the thermally generated electron is not equal to the current due to holes. Why? In current electricity, I told you there is one formula. Current is depending upon area and number of charge carrier per unit volume and the velocity or mobility, you can say. So we know that number of charge carriers will be same, number of electrons per unit volume, number of holes per unit volume will be same. But holes are in the valence band, or valence band electron are not free as compared to the conduction band electron. Or you can say the mobility of the valence band electron is not as such like the mobility of the conduction band electron. So IE is due to the electron in conduction band. IE, the current due to electron is this IE is What? IA is due to the electron in conduction band, which are free to move, and IH is due to the electrons in valence band, which are not so free to move. So you can say, in other words, mobility of hole is less than the mobility of free electron. This is completed, Nafisa? This one?
Yes, sir. It's completed.
Okay, so now you can take the screenshot. Okay, I have tried my best to explain this. I don't know how much you have understood, but you should once you should read all this again. Okay, so now you can take the screenshot.
Yes, sir. Done.
Nawal took the screenshot. Okay. Scroll down.
Yes, sir.
Okay. Take the screenshot.
Yes, sir. Done.
Okay. Okay. Done.
Yes, sir. Done.
Okay.
Yes, sir. Done.
Okay.
Yes, sir. Done. Yes, sir. Done.
Okay.
Yes, sir.
Okay. Mm-hmm. Okay. Okay, just a minute. This is very important. Okay.
Yes, sir. Done.
Okay.
Yes, sir. Done.
Okay.
Done, sir.
Complete. Okay. Okay, so in the next lecture, I will finish this chapter, and after that, if you want, then we will start the revision. And when your examinations are getting start, 24th Feb. Okay. So, are you taking the other classes? Someone is taking, I think, wave optics. Are you getting the
Yes.
notification?
Yes, sir.
So, uh, I do not know the teacher name. So, um, actually, I skipped that chapter. I thought that we will do that chapter when we will revise, but my teaching style is like I always try to uh, think that whether the syllabus is completed or not completed, but the topic that I am teaching, the student should get it properly. So accordingly, I teach you, and that is why the syllabus is not finished on time. So basically now almost we have finished, and after this lecture means after this class there will be one lecture, and this chapter will also be finished. And if you will do the revision with me, with means if we have a revision classes, so in those classes one more chapter I skipped, that is the natural magnetism. So we will continue with that. Okay. And otherwise, if you want, then uh, it's your choice whether you are joining the revision classes or not. Okay. So now time is less. Okay. So accordingly, make the schedule and give proper time to each and every subject, whether it is physics, chemistry, or math, any other subject. Okay. And if there will be the revision classes, so what we will do in that, I will take the questions of the previous board exams, and we will try to solve those questions. Okay.
Yes, sir.
Actually, mm, actually, I am teaching you all at least from, I will say, 7 or 8 months. So, uh, so during my classes, whenever I was teaching some topic, okay, whenever I was teaching some topic, maybe sometimes it will be like it is fast. Okay, sometimes I was teaching fast, but sometimes it is very slow. Okay, my teaching style is teaching not slowly but conveniently so that the student can get. Okay. But sometimes it will be difficult for the teacher. For the teacher also it is difficult. Uh, so what I want to say is that